Hello everyone, my name is Kamal and I welcome you all to my YouTube channel. So I request all of you please like, share, comment and subscribe to my channel so that you guys can know about my new videos. And the topics which I'm going to cover today is about EPR, electron paramagnetic resonance. And here I will not talk about the basic fundamental electron paramagnetic resonance, but the problem which came in the CSIR exam. So while solving those problems, I will give some details of the electron paramagnetic resonance. So some of the questions I also have taken from the Atkins physical chemistry book. Okay, so I'll cover around 10 problems. So let's see how it goes. So I'll start with the first question. So this is a very fundamental and basic question. This will also kind of explain the basic of electron paramagnetic resonance. So as you understand from the name electron paramagnetic resonance, so we are interested in a molecule where you have unpaired electrons. Okay, so where you have a resultant spin. So we are not interested in the diamagnetic molecule. We are interested in the paramagnetic molecule. Means we have a unpaired electrons. Okay. Now this is the question. The center of the EPR spectrum of atomic hydrogen lies at 329.12 milli Tesla. Tesla is a unit of field, magnetic field. In a spectrometer operating at 9.2231 gigahertz. Okay, what is the G value? Okay, so basically when you see an EPR spectrum, you will see something like this of a simple electron. The EPR should be like this, and this is the center point of the EPR. Okay, now what they have given, they have in the EPR, the peak will be like this, and then in this direction you will see a magnetic field. So this is the way people plot EPR spectrum. So you will have a spectrum, and this direction you will have a magnetic field. Now what they have given in this problem, they have given that they have said that the center point or the field, the position of the center of the peak is, they have given 329.12 millitesla, and they are asking what is the G value. Okay, so what happened basically, you know that electron has a spin magnetic moment because of its spin, which is a quantum mechanical property. Now electron has a two different orientation. For s equal to half, electron can have two different orientation, and they can have a plus half, they can have a minus half. In the absence of any field, these two levels are degenerate, but then when you apply a magnetic field, this magnetic field interacts with the magnetic moment of the electron, and because there are two different orientations are possible, so I get two different energy levels. Now if you provide sufficient energy or electromagnetic radiation to the molecule in the ground state, minus half will undergo a transition to the higher excited state, that is plus half. And when this transition will happen, so this is known as your resonance condition. The energy gap, which is known as G beta H, should be exactly equal to the energy provided by the electromagnetic radiation. So H, I think all of you know, is the Planck's constant, and nu is the frequency of the radiation. Now this energy should be equal to the difference between these two states. Okay, because of this, this is known as resonance condition, and at this condition only you are able to see the transition. So when you get the transition, you will see a peak in the EPR spectrum. Okay, now this gap depends on the field, how much field I'm applying. Based on that, the gap will depend. Okay, also on the G. Now from the resonance condition, you can see that H nu equal to G beta H, and in the question they're asking about what is the value of G. So I can rearrange the equation, and finally I will get this. So G equal to H nu by G equal to H nu by beta H. Now, H we know it's a Planck's constant. Nu is the frequency of the spectrometer. It is given 9.2231 gigahertz. So here I have converted the gigahertz into the hertz, SI unit. Then this is a Bohr magneton. I hope everyone knows this is a Bohr magneton. This is a magnetic moment of a single electron. So this is known as Bohr magneton. And then you have the field. This is a field, and the value they have given 329.12 millitesla. So I've converted the millitesla into the 10 to the power minus 3. Now you see the units. Second cancel, joule cancel, Tesla. So finally, you do not have any unit. So the value after you do the calculation, the help of the calculator, you'll get 2. Finally, so this is the G value you'll get for an electron when you measure the EPR spectrum in a instrument of this frequency, and the transition will take place when you reach to the field. Okay, before that, after that will not happen. Only at a precise magnetic field, whenever you have a resonance condition fulfilled, you are able to see the peak. So this is the first question. Here I have shown that why the energy levels are created or originated. As I said, it's a magnetic interaction between the magnetic moment due to the spin of the electron and the applied magnetic field. And depending on the F value, okay, because for free electron it's only S equal to half, so I will get 2 different MS levels. So based on that, I will get the energy levels. So finally, if you know the field, if you know the frequency, you can easily calculate the G value for the complexes. Okay, let us move to the, okay, one more important thing I like to tell. This is the selection rule. The selection rule is that delta MS should be plus minus 1. Okay, this is the one important things to note. Okay, let's move on to the next problem. Now this is problem came in the CSIR exam, and they are saying EPR spectrum of a free radical containing nuclei with a non-zero nuclear spin is obtaining if the following selection rules are observed. So they have given 4 selection rules. Out of the 4 selection rules, which selection rule is satisfied, has to be satisfied to get an EPR spectrum. Now, this is exactly similar what I have explained in the earlier slide. So you have free electron, and then you split the 2 levels in the presence of a magnetic field. Now, what happens when you have a nucleus with a non-zero nuclear spin? Now, to explain this, I have taken a simple example, hydrogen, for example, hydrogen radical. Now, hydrogen radical, the nucleus also has a spin that is known as nuclear spin. Okay, because of this nuclear spin, they also have a nuclear magnetic moment. Okay, now the value of the nuclear spin of hydrogen is I equal to half. So basically it is represented by I for the nuclear and F for the electron. Now they can also have 2 different orientations. Mi can be plus half, Mi can be minus half. So these 2 states of the nuclear spin interact with the electron spin, resulting 2 different states. Okay, now minus half level gets split into 2. Similarly, the plus half also gets split into 2. Now, the selection rule is that, as I said in my first slide, delta MS should be plus minus 1. So this is the condition, and another condition has to be satisfied simultaneously. This is your delta MI should be 0. Okay, that means I cannot do a transition from MI half equal to MI plus minus, MI minus half. So I can only only transition can happen from plus half to plus half, minus half to minus half. So you can see now the gap represents the energy. So instead of 1 signal, I will get now 2 signals. So this black color line is a signal when you do not have any nuclear spin. Okay, that means you can consider of a free electron. Okay, now when you include a nuclear spin, for example, in this case, the I equal to half. So what you get, you are start to getting two different peaks. Now this is a spectrum. So this black line will now split into two red lines. Okay, so this is known as doublet. So this single line due to free electron is splitted to two peaks, and the one will have a lower energy than your free electron, one will have a higher energy than your free electron. Okay, now in order to get these two peaks, you need to satisfy this condition. So this is important. So these are the condition. You should remember it because we are going to use it for many other cases. Okay, so I hope this is more of a kind of an information kind of question, that what is the selection rule for EPR spectrum. So this is the selection rule. MS should be plus minus 1 and MI should be equal to 0. Delta MI should be 0. Delta means we need to see the final state minus initial state. Okay. Let's move on to now next question. This is I have taken from the Atkins physical chemistry textbook. So they have given a radical containing 3 equivalent protons, shows 4 spectrum with a intensity distribution 1 is to 3 is to 3 is to 1. The lines occur at the first line is here 331, second line 333, third line 335, and the fourth one 338. What is the hyperfine coupling constant of each proton? Okay, now hyperfine coupling constant you can calculate very easily. So this gap, so as I said in my earlier slide, if you do not have any proton, so you should get only one peak, and the position of that one peak should be at the this dash red color dash line should represent the position of the EPR without any kind of interaction with the nuclei. Okay. For example, it is coupling with the 4 protons. So if you do not have any proton and only electron, you should get an EPR line exactly here. Okay. Now when you put three protons, now this line will split. Okay. Now this line will split into 4 lines, and the intensity will be 1 is to 3 is to 3 is to 4. Now what is the Hyperfine coupling constant? Hyperfine coupling constant is nothing but the distance between these two peaks. Distance between these two peaks, distance between these. Now all the distances are same. So you just subtract in order to calculate the first hyperfine coupling constant. For example, take this one 333.6 minus 331.4. So this peak minus this peak, what I will get? A value I will get. What is that value? 2.2 millitesla. Okay, so this first question is solved now. Now, what is the G value of the radical given with a spectrometer? So as I said in my first slide, in order to calculate the G value, you need to know the what frequency instrument you are using, and number 2, what is the field. Now, in order to know the field, because I know that initially the signal should be here, because of coupling it is splitted. Now, in order to determine this red color position, the field of this red color line, what you have to do, you can do 2 ways. We can take the first one and the fourth one, add them. Okay, first one and the fourth one, add them, divided by 2, you will get the middle point. Or you can take the second one and the third one and divided by 2, then you will get 334.7. So this is the field at which, for which you need to determine the G value. Okay, now you know the field from these 2 ways, and you know the instrument frequency it is given. Now you just put in the formula and you'll get the 1.99. Okay, this is very close to 2. So this is most likely this is a EPR spectrum of phase 3 radical. So this I have drawn from in ChemDraw. So keeping this thing in mind. Okay. Now in the next slide, I will explain why the different lines are coming. So what is the formula which you can use to determine the number of peaks? Okay. Now this is a question which came in the CSIR exam, and they have given a copper complex, copper ethylene diamine, and then they are asking how many lines in high resolution EPR spectrum you will get. Now, based on our earlier knowledge, it is very easy now to solve this problem. Our first job is to determine what is the spin of the copper. Copper is a D9 system and it is a 2+ ion, so its spin value is half. Now, when you have a half spin, you should get only one peak. Okay. Now, nuclear spin of copper is 3/2. That means the copper will itself split the one signal into 4 signal. Now this is the formula. If you have a signal and which is if you have a signal and that is interacting, or if you have an atom where you have an electron and that atom is interacting with the nucleus with a nuclear spin I, then you have to use this formula. So this N represents how many equivalent nuclei you have. Okay. So in case of copper, you have only one nuclei, so you just put one, and then for nuclear spin of copper is 3/2, and you just put it 3/2, and then the formula is 2 into n cross 3/2 plus 1. So you'll get a 4 here. Now each of these 4 lines will split further because of the nitrogen. So this copper is coordinated to the 4 nitrogen, and then each of the 4 line which I got due to copper will split into how many lines? Let's see. 2 into 4 nitrogen I have. Nuclear spin of nitrogen is 1 plus 1. So 2 into 4, 8 plus 1. So 9. So each of the 4 line which I got due to copper hydrogen interaction will now split into 9 lines. So in total I will get 36 lines. Okay. So this is the result, or this is the prediction based on the formula, based on the structure, that you will get 36 lines for this copper complex. Okay, so this is the formula. You should remember that if you have n equal to 1, n is the number of equivalent nuclei which have a nuclear spin and which are interacting with the electron, and then again you have this I is the nuclear spin of that atom which is interacting with the electron. So this is for the copper, this is for the nitrogen. So exactly a similar complex also came in CSIR in some different year. This is a little bit interesting. So they're saying that for a complex A, deuteration of NH protons. So here 2 NH protons are there and does not alter the APR spectrum. That means when you take the APR spectrum of this complex, then again you make another complex where you replace this proton with a deuterium. Okay, now again you record the APR. The result is that you do not see any change in the APR spectrum. Now that means that these protons are not interacting or not involving with the coupling. Okay, are not involving in the coupling or not interacting with the does not have any effect in my EPR spectrum. So I can ignore them while calculating the number of hyperfine lines. Okay, as discussed earlier, it is a copper. Now copper can have a 3/2 nuclear spin and nitrogen have a 1. Now the same formula I will use 2 into 1 because I have only one copper. What is the nuclear spin? 3/2 plus 1 according to the formula. Then I will get a 4 peaks. Now each 4 peaks will again split due to 2 nitrogens, 2, 2 into 2 into 1 plus 1. So 5 lines. So I'll get 4 lines from the copper due to coupling with a 3 by 2, and the 2 nitrogens will also couple, and finally we'll split the 4 peaks each into 5. So total I will get 20 peaks. So this is the number of peaks I will get in this complex because these protons are not interacting. So this is an experimental evidence that if you remove the protons by deuterium, there is no change in the EPR spectrum. If you see any change after replacement of the deuterium, then you could say that these protons are also interacting, but this is not the case. So in this case, you have only 2 peaks, sorry, 20 peaks you will get. Okay, this is a very complicated problem. So this, I must tell you that there is no simple way you can answer this problem. You need to have little bit of knowledge of quantum mechanics, and by giving a simple answer, that means you will cheat yourself. Don't do that. Okay. So EPR spectrum of a complex they have given, and they're saying that G parallel is greater than G perpendicular, and which is slightly greater than free electron G. So where the electron is? Now we know that copper in elongated or compressed case, there is 2 possible ways. Either the Z will go up or x square minus y square will come down. Okay, let's see. Now if you read the Drago book, okay, they will find that the formula for the Gz and Gx are like this. Okay, now here this is the free electron G value. Okay, this is a free electron G value, and this I'm considering a elongated case because of this Z is below x square minus y square. Now you see in this formula, this xi, what is this xi? This is spin orbit coupling parameter. Okay, so this is spin orbit coupling parameter is slightly different than spin orbit coupling constant. Okay, so this is always positive number. Okay, spin orbit coupling parameter can be positive, negative, coupling constant can be positive, negative, but the spin orbit coupling parameter is always positive. Okay, now this is positive, and this G value will depend between the energy gap between these 2 orbitals, and then this Gx, for this Gx, the uh, will depend on this energy levels. Okay, let us see. So why this is coming in both the cases, because this electron, or the final electron, the unpaired electron is in this orbital, so it is in both the cases it is there. Although there are more details are there, I cannot explain all the details here. It will be a little bit complicated, but those who want to know more, you can read Drago book, or I will make another video where I will explain only about these equations. Fine. For right now, for the time being, you just believe that these equations are correct. Okay, and this dz value will depend on this, and gx value will depend on this equation. Now, if you see the diagram here, the gap between x square minus y square and xy, and the gap between x square minus y square and yz. So this gap is larger. Okay, the energy is larger in this case than this one. Now, if you do inversion, if you invert it, if you do 1 by 1 by, or if you take a reciprocal, then this will become smaller and this will become bigger. Why I did that? Because in the formula I have 1 by term, so I made in this way. Now, if I multiply, because this is a positive term, I will not change the sign anyway. This is only positive. So I just multiply these 2 equations by 2 zeta. Okay, or xi. 2 zeta. Just you multiply. Now this term is smaller. This term is bigger. Now here is a positive sign. If you have this term in the equation is bigger, obviously the z will be bigger. Now if you have a term which is smaller compared to this one, okay, because this term is smaller than this one, and you know why, you can easily calculate based on this energy splitting diagram that this term is bigger than this one. So obviously the GZ value will be more in higher, GZ value will be higher than GX and GY. Okay, so this is the way. So those who are interested to know when it will happen that G parallel or GZ will be smaller in smaller than G perpendicular, they can just calculate using the same equation and just reverse it and draw a new splitting diagram for the compressed case and then see. Okay, so that is the kind of a homework for you guys. So I hope now you understood that the real answer of this is a little bit difficult because you need to know about quantum chemistry and those things. So, but you cannot change the truth. So whatever is the truth is the truth. So if you want to know really how it happened, you need to read about quantum chemistry. But if you don't want to read, you have to believe that these equations are true, and then you just carry on, and finally you will get the results. Okay, this G parallel is greater than G perpendicular. Now the electron has to be in the x square minus y square orbital. Fine. So this was a little bit difficult. Let's move to an easy problem. So this is came in some year, I don't remember the year, in CSIR exam. Very simple. Manganese 2 high spin complex, so S equal to 5/2, and you know this is the electronic configuration. Now for this configuration, you can calculate the term symbol. It is 6s. Now you have a 5/2. What will happen because of the zero fill splitting? Your the degenerate 5/2 level S equal to 5/2 will have a total plus minus 5/2, 3/2, and half. So these many levels will be there, but they are degenerate without if you do not have any zero fill splitting. But if you include a zero fill splitting, these levels will split. Okay. Now when this level will split and you apply magnetic field, you will get splitting. Okay. Now if you follow the selection rule which I have explained, delta ms equal to your plus minus 1, you will see that you can get 5 different transitions. Okay, from minus 5/2 to minus 3/2, then minus 3/2 to minus half, then this one, then this one, this one. So this is based on your selection rule without involving any nuclear hyperfine coupling. Now this kind of transitions are known as fine structure or fine lines. Okay, when you have EPR signal without the application of without involving any nuclear coupling, hyperfine coupling, then that kind of peak, those lines are known as your fine line. So this question they have given how many fine lines. So total you'll get a 5 lines. Okay. So you can see here if you apply the selection rule, you'll get 1, 2, 3, 4, 5. So 5 peaks you'll get now because of the nuclear spin. It has a I equal to 5/2. Now each level will split into 6 lines. So I hope you guys remember the formula 2ni plus 1. So if you use that formula, so you'll get 6 lines. So every peak, so you should have ideally 5 peaks, 1, 2, 3, 4, 5. But then due to the presence of a nuclear hyperfine interaction, each peak will split into 6 lines. Okay, so the total hyperfine you have 30, and fine you have 5 lines. So again, I'm telling that the fine line comes when you do not apply any nuclear coupling. Okay, nuclear hyperfine coupling. So you just apply the magnetic field and measure it. Okay, so of course we cannot do in reality. So reality, if you see, we have five bunches of uh, six slitted nuclear hyperfine slitted. So you can calculate from that, or you need to draw a very perfect energy splitting diagram. From there, you just apply the selection rule, and then you'll get the answer. So the answer for this question is 5 and 30. This is very important. So you got to know the information about the fine structure and hyperfine again. Now I don't know why they have given this problem. The CSIR people should not give this kind of problem. These are very confusing problems because you can think of several ways to answer this, but we'll take the simplest route. No zero field splitting, nothing, because in the question they have given no information, only the nickel complex is said. Now for the nickel, this is the electronic configuration. So we have a T2J6 and Eg2, that means S equal to 1. Now S equal to 1 means you have how many MS states? You have 3 MS states, plus 1, 0, minus 1. Now in the presence of a magnetic field, the 0 level will not have any influence on the magnetic field, but your minus 1 and plus 1 will get separated. Now if you apply your selection rule, delta MS equal to plus minus 1, you can get two different transitions from minus 1 to 0 and 0 to plus 1. But if you see the energy, here also it is G beta H, here also it is G beta H. So you will get only one peak. Okay, even though two transitions are possible, but the peak position is same. That means you have this peak for this transition also, and the another peak for this transition, but both the peaks are overlapping on the top of each other. That means both the peaks have the same energy. So the number of observed, okay, possible you have two, because there's two possible transitions, but the energy is same. But observed, you will get only one peak for this nickel octahedral complex. So the answer is 1. Okay, so here I have not included any zero field splitting, nothing, because in the question they have said nothing about the zero field splitting. Okay, now this is a more of a memory kind of question. This also came in CSIR exam. The reduced form of a metal M is NMR active, and on oxidation, the complex gives an EPR signal, which is G, this much, and Mosby spectroscopy cannot characterize the complex. So I cannot use Mosby spectroscopy as a tool for the complex, which metal it is. Okay, now let us see one by one. Zinc. Now zinc has a nuclear isotope where you can have a NMR active. Zinc is diamagnetic compound, inactive. Zinc is also Mosby active, and this is the electronic configuration, so there is no way you can get any paramagnetic. So EPR is, and it has a nuclear spin of 5/2. Tin, obviously NMR active. EPR is not active because this is the electronic configuration. You can have two, you can have your type P2. The problem is that when it form bond, either it will form SN2 plus or SN4 plus. So when you do this kind of bonding, this electron will go. Ultimately, there is no unpaired electron. Copper, famous, everybody knows. Copper is NMR active, EPR active, Mosby inactive. Okay, copper is Mosby inactive, and it has electronic configuration. Iron, NMR active, EPR obviously, it has unpaired electron. The iron is also Mosby active because in general iron 56 I equal to 0, but iron 57 is the most of active. Okay, now this is the electronic configuration. So the only thing that this is NMR active. Okay, fine. Oxidation, copper. If you oxidize, you can get copper 2 plus, copper 3. All are if you're active, but unfortunately, this if you are inactive. And finally, this is the answer. Okay, so this is very important, and that which metal. So this question is telling you that if you have a metal, what kind of experiment you can do, which experiments are possible and which experiments are not possible. Thank you for this one. This is a very interesting one, and this is a very common question in CSIR exam or GATE exam. They will give a vanadium compound, and then they will ask that how many API lines will come. The important thing is to know that at what temperature they're asking. Are they asking at a room temperature or asking at a low temperature? If at a low temperature, then you'll get an isotropic signal. Otherwise, it's a so the first thing to determine the oxidation state. What is the oxidation state? Now this vanadium you have coordinated to this oxygen. This is 2 negative, and each of your acetyl acetonate is 1 negative. So 1 negative, 1 negative, 2 negative. Again, you have 2 negative from here. So total you have 4 negative. So the charge on the vanadium is +4 oxidation state. So it's a D1. That means it's equal to half system. So it should give 1 EPR signal. But you can see that it has a nuclear spin of 7/2. The vanadium has a nuclear spin of 7/2. Now this 7/2 again with the help of same formula 2Ni plus 1 equal to, we can get 2 into 1 because we have only one nuclei into 7/2 is the nuclear spin of vanadium plus 1 according to the formula. Finally, you'll get 8 lines. So each line will get split into 8 lines. But the problem is that in solution, because this complex is not isotropic system, so you have an axial direction and you also have a perpendicular direction. Okay, so this is known as your Z parallel direction, and then you have a Z perpendicular direction, Z action. So because of unsymmetrical nature of the complex, you get two different types of G. Gx and Gy is same because X and Y directions are same, and the Z direction is different. So you will get two types of G value. Okay, two types of G value, and each G line, each spectra will split into 8 lines. So the answer is it is a two types of G and 8 lines. So the answer is A and D. The first one is the answer. The important thing, first to determine the oxidation state, I found S equal to half. Then I just calculated this. When we look into the structure, you can easily understand that this is an axial system. In axial system, you will get a two type of G, Gx and Gy, which is not equal to Zz. Finally, so you'll get one peak corresponding to these two G's, which will be exactly at the same position, and another one is a different place corresponding to Zz. So I hope these are the problems which I have described in this video. These all I have taken from the CSIR exam and the Astute Physical Chemistry books. If you guys have any doubt relating anything, please feel free to ask me anything. I'll be happy to answer any of the questions, any doubt. Okay. Also, I can refer any books where you can read the section and understand by yourself from where I have taken the answer. Okay. Thank you, guys. Bye bye. For right now. So once again, I will say that please subscribe to my channel.